All right, here we are in Chapter 5. We're going to be talking about hypothesis testing. And before we even jump into it, I want to just kind of contextualize this because sometimes people will look at the content of the chapter and get bogged down by it. Here's the basic idea of what we are doing in Chapter 5. We are going to see if a score is significantly different than other scores. That's it. Imagine this. You are taking an exam in a class, and we know that the rest of the class averaged an 80. We want to know if your score of a 90 is significantly different than the rest of the class. That is the core logic of what we're doing here. That's the only goal that we have, is to determine if a single score is significantly different than the rest of the scores. If you keep going back to that idea, you're going to do a lot better than getting bogged down by all of the other stuff that we're going to be talking about. So be sure to remember that that's the goal, and that the rest of this will be a little bit easier if you can continually go back to that. So let's jump right into it, and let's review the symbols real quick for the population and for the sample. The sample mean is capital M, sample variance is SD squared, standard deviation is SD. The population mean is mu. The variance is sigma squared, lowercase sigma squared. Standard deviation is lowercase sigma. The population is the individual group, or excuse me, I shouldn't say it like that. The population is the group that we are comparing our score to. The sample is the score of interest that we are comparing to the population. Some important terms for you to be paying attention to in this chapter are theory, research question, hypothesis, which is also kind of alternate in research hypothesis. So the hypothesis is made up of two sub-hypotheses. The null hypothesis, the comparison distribution, and the cutoff score. So make sure that you're paying particular attention to those. If you have questions about those individually, reach out. But I think that by the time we're done with this and the reading, you will have them down. I like to start out with an example to kind of give you a context of what we're doing before we jump into things. That way, when I talk about numbers and ideas, I can tell you what it relates to in the context of the example. So this is an example from the book. The example is this. Babies are given a vitamin. One group of babies is given a vitamin that does nothing, kind of called a placebo. One baby is given an enriched vitamin to see if the vitamin has an impact on the walking age. Below is the curve determining the distribution of babies who took the placebo. So the population in this case is the babies that took the vitamin that did nothing. That's the larger group of babies. There is one of those babies who was given an enriched vitamin. We're going to see if that baby that took the enriched vitamin walks at a different age than the babies that were given the regular vitamin or the placebo vitamin. Okay? Our distribution looks like this, and I put the percentages on there as a reminder just to kind of generally show you what the breakdown is. I won't do that forever, but just while we're learning this and getting the hang of it, I'll leave it there. The average number of months that babies walked was 14 and a standard deviation of 3. You can tell that because the mean is 14 and the first standard deviation is 17 months, meaning that the standard deviation is 3 months. The mean z-score is 0, as all z-scores are, and the standard deviation for the population, which is measured by lowercase sigma, okay, the sigma is 1. So the standard deviation of the z-scores is 1, meaning that the standard deviation of the z-scores for the population is 1. Positive 1, positive 2, negative 1, negative 2. We'll come back to this plenty. So let's just talk about this a little bit. We have a distribution that has a mean of 14 and a population standard deviation of 3. And this is that replicated table from last slide. Let's just talk about this for a second. At what age would you expect babies to walk? Well, if you had to guess, you would say, well, probably 14 months. But within reason, based on the data that we have here, what do you think? Are you thinking between 11 and 17 months? Because if you thought that, you'd be thinking that, 68% of babies walk between 11 and 17 months. Are you thinking maybe 8 to 20 months? That would mean that 96% of the babies walk between 8 and 20 months. Okay. What would you think about a baby that walked at 6 months? Well, it looks like 6 months is, lower than -2 standard deviations. So it looks like that would be, a low probability, meaning that the baby would probably walk less than 2%. That would be the probability that the baby would walk at around 6 months. It'd be less than 2%. What if I said that the reason that the baby walked at 6 months was because that's the one that took the vitamin? Okay, now we're starting to think maybe the vitamin has something to do with it. So if you see a baby that walked at 6 months and that's the baby that took the special vitamin, you might think that the vitamin has something to do with it. Another question is, how early would the baby need to walk before we consider the vitamin the reason? That's interesting. If a baby walked at 11 months, would you think that that baby was the one that took the vitamin? I don't know. Maybe, maybe not. That's, there's still 16% of babies that walked even earlier. What if the baby walked at 12 months? Okay, that's not any closer, but maybe, I don't know. What about if the baby walked at 8 months? Okay, now we're starting to think that if a baby walks at 8 months, that baby might be the one that took the vitamin. Okay, when we're thinking about this, we're thinking about what's the likelihood that a baby walks at a particular age, and if that likelihood is very small, then they probably are the ones that took the vitamin. Now, we're really going to know what the baby who took the vitamin's walking age is. We'll know that, so we'll be able to determine if that's the baby that took the vitamin. But the real question is, if the baby that took the vitamin walked at 11 months, would we think that the vitamin made a difference? The answer is probably no. But if that baby walked at 8 months, maybe it is. Let's keep going forward. Hypothesis testing is how we determine if our results are expected based on the comparison distribution. There's a couple of terms in there you got to kind of wrap your head around. The comparison distribution is the group that we are testing our sample to. So in the case of our baby walking example, the comparison distribution is the rest of the babies. We're comparing our score for the baby that took the special vitamin to the comparison distribution. Another way of saying that, are the results we saw different from what we would expect if there were no difference? Boy, that sentence sounds inside out, but unfortunately that's actually accurate. So, are the results that we saw different from what we would expect if there were no difference? In the baby walking example, let's say that the baby walked really early, and let's say it was 6 months. Are the results that we saw, the baby walking at 6 months, different from what we would expect if there were no difference? Is 6 months significantly different than the rest of the babies in that distribution? Okay. A very concrete example of the difference between the alternative and the null hypothesis is an egg dying example, like an Easter egg. So let's start with the alternative hypothesis. That egg is blue, it's been dyed. This egg is different than an egg that has not been dyed. The comparison distribution, in this case, is an undyed egg. So a regular old white egg. We know that this egg is dyed, not because it is dyed, but because it's different than an egg that is not dyed. Now, obviously, in our heads, we skip the logic that says that, well, that's not the same as an undyed egg. It just is blue, so it must be dyed. But the logic is that it's blue. It means it's different than the white egg. It means that it's different than what we would expect if there were no effect or there were no difference. So, a blue egg is dyed. And we know that because it's different than the egg that is not dyed, the null hypothesis. The null hypothesis is related to the comparison distribution. The comparison distribution is a group that has no treatment to it. In the baby walking example, the babies that took the regular vitamins, not the super special vitamin that the other baby took, but the regular vitamin, that is the null hypothesis group. That is the group that we would expect our baby to look like if the walking age were not impacted by the supervitamin. The alternative hypothesis is that the baby will walk at an earlier age because of the vitamin. It will be different than the null group, the comparison distribution. We're going to keep going forward, and we're going to make some sense of this as we put the example together. When we have hypotheses, we have two hypotheses. It's called a hypothesis set. We have H sub 1, which means alternative hypothesis. In our example, the alternative hypothesis is what we expect to happen if the baby that walked at a particular age because of the vitamin is significantly different. It's stated like this. Babies with the enriched vitamin, in this case it's one baby, but the baby with the enriched vitamin will walk sooner than those with the regular vitamin. Okay? I'm going to just fix the typo real quick. Babies with the enriched vitamin will walk sooner than those with the regular vitamin. Just rest on that for a second. Wrap your mind around it. Another way of stating that is babies with the enriched vitamin will be less than babies with the regular vitamin. Remember that we're measuring this in terms of the number of months that the baby first walked. Okay? Babies with the enriched vitamin will have a lower walking age than babies with the regular vitamin, meaning that that baby will walk sooner. The null hypothesis is the hypothesis that is true if there is no difference. So if the vitamin didn't make a difference in the walking age, then babies with the enriched vitamin will walk at the same age or not significantly different than those with the regular vitamin. The null hypothesis has some wiggle room in there. Babies don't have to walk at exactly 14 months in order to be like the null hypothesis group or the comparison distribution. All they have to do is not walk very much differently than those other babies. That's why we kind of talked about what would you think if a baby walked at 8 months or 10 months or 11 months. The baby can still walk at a different age than the mean of the other babies and it still be non-significant. Another way of stating this is the null hypothesis is that babies with the enriched vitamin will walk at a greater or equal to age than the babies with the regular vitamin, meaning that they will walk at about the same age or later than babies with the regular vitamin. Remember, the null hypothesis is what we would expect if there were no difference between the test group and the comparison distribution, which we can kind of call the control group. Now, we have to go through a series of steps in order to determine if there is a significant difference between the baby that walked with the supervitamin and the babies who took the regular vitamins. We use 5 steps to do that. The first step is to restate the question as an alternate hypothesis and a null hypothesis, and to identify the populations, which we will call the sample and comparison groups. The second step is to determine the characteristics of the comparison distribution. We need to know what the group that has no treatment effect looks like in order to compare our sample to. We need to have a group that is just usual or normal, regular, whatever you want to call it. We need to have that group available to compare our results to see if it's different from that group. Step 3 is to determine the cutoff score. We will reject the null hypothesis. Okay, there's some terminology there we need to wrap our heads around. But especially once we get into that step, it'll make more sense. But the cutoff score is the z-score that we're going to use to determine if our sample's z-score is different than the rest of the other scores. And in that case, we will reject or fail to reject the null hypothesis. Again, we'll get into that a little bit later. Step 4 is to determine the sample's score on the comparison distribution. Once we develop the comparison distribution and we find out the score that we're going to use to cut off our result, we need to find what our sample score looks like on the comparison distribution. And again, we're using z-scores for that. Then the last step is to determine whether to reject the null hypothesis or not. So let's continue with our example. Step 1 is to restate the question as an alternate hypothesis and a null hypothesis, and identify the populations. The research question is really, does the baby who takes the enriched vitamin walk at an earlier age than those who take regular vitamins? We have two populations of interest here. And this is kind of another one of those examples where I wish the book would use different terminology. It should really be groups. But that's okay. We can roll with this for now. Population 1 is the baby that took the enriched vitamin. That's one single individual baby that took an enriched vitamin. Population 2 are the babies who took the regular vitamins. So population 2 is going to be our comparison distribution. All the babies who took the regular vitamins, we know that they have a particular walking age on average with the standard deviation. We'll look at that in step 2. The alternate hypothesis for this is that babies with the enriched vitamin will walk sooner than babies with the regular vitamin. Again, it's one single baby with the enriched vitamin. Another way of saying that is that population 1 will be less than population 2. Population 1 is the enriched vitamin baby. Population 2 is the regular vitamin babies. We think that the baby with the enriched vitamin will walk earlier than babies in general. The null hypothesis, which is the hypothesis that we're going to use for testing, is that babies with the enriched vitamin will walk at the same age or later than babies with the regular vitamin, meaning that our baby, if the null hypothesis is true, will have a walking age that is about the same as the rest of the babies. Step 2 is to determine the characteristics of the comparison distribution. The comparison distribution is based on the babies from the example that took the regular vitamin. We are going to see if our baby that took the enriched vitamin is significantly different than our comparison distribution. The babies that took the regular vitamin has a mean of 14, which is indicated on our normal curve. The standard deviation is 3. So we add 3 to 14, that gets 17. We add 3 to 17, that gets 20. 14 minus 3 is 11. 11 minus 3 is 8. This is our comparison distribution. Our z-scores are listed on top. Okay, it has lowercase sigma, meaning that those are our standard deviations. So 0 standard deviation, -1, -2, +1, +2. So we have our comparison distribution that we are going to use to determine if our baby walks significantly earlier. Step number 3 is to find a cutoff score where we will reject the null hypothesis. The cutoff score is the z-score on our comparison distribution where we will determine if our result is significant. We are going to use a cutoff z-score equal to -2. Something that you will need to understand is that -2 is not what we call a conventional cutoff score. We're using a z-score cutoff of -2 for the sake of the example to make it a little bit neater. Okay, so when we have a cutoff score, what we are saying is if the z-score of our baby's walking age is lower than or less than this cutoff score, we will reject the null hypothesis. We'll review that in a second. If the z-score for our baby is greater than or equal to our cutoff of -2, so if it's greater than or equal to, then we will fail to reject the null hypothesis. Let me go back to the null hypothesis real quick. Our null hypothesis was that population 1 will be greater than or equal to population 2. What we're really saying here is, will our population 1 z-score, which is the z-score of the baby that walked at a particular age who took the vitamin, will that be greater than or equal to population 2, which is our cutoff score? So we are going to say, is our z-score from our baby greater than or equal to our z-score of our population? And that's indicated here. Will the z-score of our baby be greater than or equal to our cutoff z-score of -2? Okay. I have created this red kind of backwards L shape to indicate that if our sample's z-score falls anywhere in this red zone, then we can reject the null hypothesis. We can reject the idea that these two groups are the same. we will reject the idea that our baby walked at an age similar to the rest of the comparison distribution. There are a few different ways to say it, so I might say them repetitively using different terminology, but they are the same. So now that we have our comparison distribution, and we have a score that we are going to use to determine if our result is significant, we need to find out what the actual z-score is, or the number of standard deviations above or below the mean our baby who took the enriched vitamin is walking at. And we do that using a usual formula. It looks a little bit different though. I brought forward some information. We knew that the population mean was 14. We knew that the standard deviation was 3. But now we have an x-score. This x-score is the score from the baby who took the enriched vitamin. The baby who took the enriched vitamin walked at 6 months of age. Okay? Now, 6 months of age isn't listed here in the number of months. We recognize that it's below 8, so you might be jumping to your own conclusions right now, but just bear with me for a moment. We need to convert 6 months to a z-score to find out if the z-score for our 6 months is less than our cutoff z-score of -2. So we do some math. We use a z formula that says z is equal to x minus mu divided by sigma. What that really means is z equals our raw score minus the population mean divided by the population standard deviation. You recognize this form from last chapter where we did x minus m divided by SD, which was x minus mean divided by standard deviation. This is the same formula that we're using. It just uses population mean and population standard deviation. We plug in our number. Z is equal to 6 minus 14 divided by 3. That's 14 is the mean. Standard deviation is 3. And we get -8 divided by 3 equals -2.667. Our sample's score is 2.667 standard deviations below the mean. Okay? Again, you might be jumping to your own conclusion, but bear with me. As a reiteration, in step 5, we're going to decide whether to reject the null hypothesis. And as a reminder, our decision was to reject the null hypothesis if our sample score was less than z equals -2. So our cutoff z-score was -2, and our decision was to reject the null hypothesis if our sample z-score was less than -2. Let's take a look and see what that looks like. We brought forward our null hypothesis just as a reminder. Babies with the enriched vitamin will walk at the same age or later than babies with the enriched vitamin. Another way of saying that is that population 1 is greater than or equal to population 2. Now remember, we are using the null hypothesis because we need to determine if our Easter egg is died by comparing it to our comparison distribution. We need to know if it is different than the distribution that has no effect. We need to determine if our baby who walked with the enriched vitamin is different than babies that walked with the regular vitamins. Our sample's z-score is -2.67, meaning our baby walked at an age that is 2.67 standard deviations below the mean. That looks pretty bad for a null hypothesis. We might get to reject it. Our sample's z-score was -2.67. Our cutoff z-score was -2. The sample, which is population 1, had a z-score of -2.67. The comparison distribution, which is population 2, had a z-score of -2. We used the null hypothesis formula in order to determine if we have a significant result. So we brought down this inequality that said population 1 will be greater than or equal to population 2. If population 1 was greater than or equal to population 2, then we would not have a significant result, as you can see here. Okay, if our sample's z-score was greater than or equal to population 2, our sample would behave like the rest of the population and it would not be significant. However, our sample's z-score of -2.67 was not greater than or equal to -2. So here's the decision. Is -2.67 greater than or equal to -2? The answer is no. If the answer is no, then we can reject this idea. We reject the idea that our sample had a score that was greater than or equal to our comparison distribution's cutoff score. We reject the null hypothesis. We reject the idea that babies with the enriched vitamin will walk at the same age or later than babies with the enriched vitamin. Oops. Looks like I made a mistake all the way through. I'm going to fix it here. That should say regular vitamin. Oh, I paused it real quick. It looks like I'm off the hook. I don't think that I made that mistake anywhere else. If I did, please forgive me. It should be the enriched vitamin babies walk at the same age or later than the babies with the regular vitamin. So if I made that mistake earlier, forgive me. So we have our decision, and we need to put it into a plain language paragraph. So let's look at what that might look like. We conducted a z-test to determine if there was a significant decrease in walking age between the baby who took an enriched vitamin and the babies who did not. The z-score of the sample was less than the cutoff z-score based on the comparison distribution. Another way of saying that is that the z-score of the sample is equal to negative 2.67. The z-score of the cutoff is equal to negative 2. These results indicate that there is a significant decrease in walking age between the baby who had the enriched vitamin and babies who did not. So for our entire example, it can be summed up with that paragraph. Going on in the chapter, it's worth noting that the example that we just did was called a one-tailed test, meaning that we were interested in a significant difference in only one tail. Okay, we were only interested in knowing if our results were significant below one cutoff value. There are other examples that we will use that have an interest in the positive tail or in both tails at once. When we use one-tailed tests, we are concerned with a negative tail or a positive tail. A two-tailed test is when we are interested in looking at a cutoff in either direction, meaning that if we are interested in knowing if our score is either significantly greater or significantly lower than a particular population. Let's take a look at what that might look like kind of graphically in terms of our cutoffs. When we talk about one-tailed and two-tailed tests, we also need to talk about probability. When you see something like p is less than 0.05 or p is less than 0.01, what we're saying is we will reject the null hypothesis if our result occurs less than 5% of the time, or p is less than 0.05. Or you could also use an even smaller cutoff by saying we will reject the null hypothesis if our result occurs less than 1% based on the comparison distribution. If we have a probability of less than 0.05 in a one-tailed test, our cutoff will be at a particular point. What's important to know here is that if we have a cutoff of 0.01, that means that our cutoff is even lower, meaning that we have a smaller likelihood of rejecting our null hypothesis. By the way, because it's a one-tailed test, this could also be the positive side, but for the sake of the demonstration, I only looked at the negative side. You would, if it were a positive test, like if you wanted to know if somebody were significantly taller than the rest of his classmates, then these two would be on the other side. We would be determining if our result was significant at a higher rate or a greater rate than our population. For a two-tailed test, what we end up doing is having two cutoff zones. So we have a cutoff zone on both sides of the curve. When we have a 1% test, that cutoff zone is even smaller because we are interested in only 1% of the entire area under the curve. For a one-tailed test, we use either negative or positive, but for a two-tailed test, we use both sides simultaneously, and you'll see what that looks like here in just a few moments. When we talk about one-tailed and two-tailed tests, that is synonymous with directional and non-directional test. A directional test is another name for a one-tailed test. We are interested in looking at a change in a direction or another. A non-directional test is when we aren't concerned with one direction or another, but we are looking for a significant change in either direction. So More precisely, probably it should be called an either directional test, but that really doesn't roll off your tongue like non-directional. This top set of hypotheses is what you would write if you were going to use a one-tailed or directional test. The alternative hypothesis for a one-tailed test is population 1 is less than population 2. The null hypothesis is population 1 is greater than or equal to population 2. However, if you were interested in a positive change, you would use the second set. Remember, when we are looking at one-tailed versus two-tailed test, it could be negative or positive. So when you are developing your hypotheses for a one-tailed test, the test has to be either negative, which is what this is. We want to see if our score is less than or more negative than a particular cutoff score. But if it's positive, then we want to know if our score is greater than or more positive than a particular cutoff score. So these two, well, I can't highlight that. These two are a set, and these two are a set. When we're concerned about significant differences in either direction, we use a non-directional hypothesis. We're going to go on with an example that wonders if the baby walked at a different walking age than the rest of the babies, not higher or less than. We want to know, not greater than or less than, but we want to know if there's just a different anyways. So we're going to end up using this type of hypothesis set. Oh, I made an error. You saw that. There you go. Should be H sub 1, not H sub 0 twice. So the alternative hypothesis is that population 1 just won't be the same as population 2. So what that means is that it's not going to be the same, so it could be either greater than or less than population 2. And the null hypothesis is that population 1, which would be our sample, will be the same as our population 2, which is our population. I have a little cheat sheet developed. As a matter of fact, one of my students developed this cheat sheet, which is kind of cool. But you can use this cheat sheet to help you organize the symbols that you would use for your hypotheses. When you have a one-tailed test and it's a null hypothesis, you use either the less than or equal to or greater than or equal to symbol. If you have a one-tailed test and it's an alternate hypothesis, then you use the less than or the greater than. If it's two-tailed and it's a null hypothesis, you use the equal sign. And if it's a two-tailed alternate hypothesis, then you use the is not equal to sign. This is a cheat sheet for this information here. That just helps you to organize a little bit. Now, we talked about P is less than 5% or 1%. In social sciences, we rely usually on the 5% critical value or 5% cutoff value or 5% alpha level. They're all the same things, just different ways of saying them. But when we have a one-tailed test, we're generally concerned with 5%, meaning that we want to know what the bottom 5% of all the scores are in our comparison distribution. And if our sample behaves like the bottom 5%, then we think that our sample is probably different than the population, meaning that it is so unlikely at 5% that we get the result that we did, then we think that our sample is different. In this case, usually it's because the baby walking age is impacted by the vitamin. So we would say that the vitamin made an impact. Now, when we have a two-tailed test or a non-directional test, we are still concerned with 5%. But what we do is instead of looking at 5% on one side, we look at 2.5% on each side. So we still have a 5% cutoff, but we are going to split the significance between the two sides of the curve. So that if we have a result in the left side that is significant, we still have an overall significance of 0.05, but it's probably going to be the actual probability of getting that particular result will be, less than 2.5% probably. But all we're saying is that we have a probability, an overall probability of less than 0.05 that we get the result. Now, the interesting thing about determining the cutoff areas for each test, for z-tests, is that there are really only several options for the cutoff z-scores. Remember from our last example, we use a cutoff z-score of 2. It was -2. Rather than using an actual cutoff z-score, just like a round number, what we're going to do is we're going to say if our result occurs less than 5% on the cutoff, or excuse me, on the comparison distribution, we will consider it to be significant. Well, what we would normally do is find where 5% is on our z table and then split that significance in half. We get 2.5%. So then we got to go find 2.5% on the z table and find out what the z-scores are and then report those. That's kind of a headache, and it's really not necessary for what we're going to do. So I will save you some work. When you want to know what the cutoff z-scores are for a particular test, you can use this table here. For example, let's say that we had a two-tailed test at the 1% significance level. We go to two-tailed test, 1% significance level, and we would use cutoff z-scores of negative 2.58 and positive 2.58. Remember, if it's a two-tailed test, we have two rejection zones. If it were a one-tailed test at the 0.05 level, we would use either negative 1.64 or positive 1.64 depending on the direction of the hypothesis. If you thought that the score was going to be less than the population, if you thought the sample score was going to be less than the population, then you would use a cutoff z-score of negative 1.64. If you hypothesized that your cutoff z-score would be greater than the population, the comparison distribution, you would use a cutoff z-score of positive 1.64. Let's go with an example. We're going to use the same kind of scenario, but we're going to change the parameters just a little bit. The research question is this: will an enriched vitamin affect the walking age of a child? Believe it or not, that statement tells you if this is a one-tailed or two-tailed test. I am asking you if the enriched vitamin affects the walking age of a child. Am I suggesting that it increases? No. Am I suggesting that it decreases? No. I'm just saying that it will affect it somehow. That is language that indicates that there is a two-tailed test, which means that we are going to set up our hypothesis to include the possibility that the baby will walk greater than a certain cutoff and less than a certain cutoff, just in case either is true. Let's say that we noticed that a baby took the enriched vitamin and walked at an age of 19 months. We're going to use the cutoff probability of 0.05, meaning that we are going to consider a result significant if it occurs less than 5% of the time, or if it falls in a rejection zone that encompasses 5% of our comparison distribution, which we'll see in just a moment. But let's walk through the 5 steps to make a decision. Step 1. We need to restate the research question as a null and alternative hypothesis and identify the populations. Population 1 is the baby that took the enriched vitamin. Population 2 are the babies who did not take the enriched vitamin. Remember, this is a two-tailed test, so we need to use the symbols that coincide with the two-tailed test. That was back here. So a two-tailed test is going to use the equal sign between the population and sample for the null hypothesis, and the not equal to sign for the two-tailed test between the sample and the population. So the alternate hypothesis is the baby that took the enriched vitamin will have a walking age that is significantly different from the babies who did not take the enriched vitamin, or population 1 will not be like population 2. The baby that took the null hypothesis is the baby that took the enriched vitamin will have a walking age that is not significantly different from the babies who did not take the enriched vitamin. So if the null hypothesis is true, then that means that there is no effect that the vitamin has, or at least not a significant effect, and the baby that took the enriched vitamin will behave like the babies that took the regular vitamins. So step 2 is to determine the characteristics of the comparison distribution, and we're going to work from the same example as earlier. We just changed the parameters a little bit. So the baby walking age on average is 14 for those that took regular vitamins. with the standard deviation equal to 3. This is the same information from last time, not going to go over it in too much detail. Step number 3, we need to determine the cutoff score on the comparison distribution where we will reject the null hypothesis. Well, we know that we have a two-tailed test and that we're using a probability cutoff of 0.05. So we're going to use two cutoff areas, negative 1.96 and positive 1.96. Remember, this is kind of just a cheat sheet that was put together for you from the book that allows you to use a table to determine what your cutoffs should be. You could use the normal curve table and determine that, but we're going to save you some work. So I have put the rejection zones here. So our rejection zones are negative 1.96 and positive 1.96. So if our results occur less than 1.96 or greater than 1.96 according to the z-score, then we can reject the null hypothesis, which means that we have a significant result. If our results have a z-score that fall between negative 1.96 and positive 1.96, then our results are much like the population and we fail to reject the null hypothesis. We want to reject the null hypothesis. That means that we would have a significant result. Step number 4 is to determine the sample score on the comparison distribution. So where does the sample score actually fall? If a baby walks at 19 months, we need to convert that to a z-score in order to compare our cutoff score to our sample score. We use the same formula as earlier. We want to find out how far away our sample score is from the mean. So we take our sample score minus the mean of the population, and then we want to find out how many standard deviations on average that is away from the mean by dividing it by the standard deviation. Z is equal to the sample score of 19 minus the population mean of 14 divided by the population standard deviation of 3. Our z-score is equal to 5 divided by 3, which is equal to 1.67 positive. Our sample's z-score is 1.67 positive, which falls about there in a comparison distribution. So as we look at this visually, it looks kind of good for the null hypothesis. The null hypothesis says that these two groups, the sample and the population, will be the same, or at least the sample won't be significantly different. So far, it looks pretty good for the null hypothesis and not being able to reject it. Let's take a look at step 5 to actually put it together. We need to decide whether to reject or fail to reject the null hypothesis. We do that by bringing forward the null hypothesis and kind of using the same symbols. So the null hypothesis was that the baby that took the enriched vitamin will have a walking age that is not significantly different from the babies who did not take the enriched vitamin. So remember, our comparison distribution is based on the babies that took the regular vitamin. Our sample's z-score falls outside of the rejection zone. So it looks pretty good for the null hypothesis. Another way that we stated the null hypothesis was that population 1 would be equal to population 2. When we have a two-tailed hypothesis, we have to do a little bit of mental gymnastics in order to make the comparison between the numbers, but I think we can do it and we can use the logic. So the sample, which is the population 1, has a z-score of 1.67. The comparison distribution has a cutoff z-score, and pardon me, that should be negative 1.96, and this should be positive 1.96. My mistake. You probably were looking at that and thought it was wrong and were waiting for me to change it. What this looks like is our sample's z-score greater than the cutoff on the negative side and less than the cutoff on the positive side. Remember, our null hypothesis states that these two are the same, that these two groups are the same. And we are testing that. We want to know if they are the same. So what we do is this. We take our negative cutoff score and we plop it right at the beginning of the equation. We make a comparison between that cutoff score and our sample's z-score, which is 1.67. The comparison is our sample's z-score, which falls somewhere, is it going to be greater than or equal to this cutoff? We also want to know if our sample's z-score is less than or equal to this cutoff. What that really means is our sample z-score somewhere between these two cutoff scores? And when we do this using inequalities, this is what it looks like. Is our sample z-score, does it fit between our negative cutoff and our positive cutoff? So we use our negative cutoff. Is that cutoff less than or equal to our z-score? And is the positive cutoff greater than or equal to? If we do it linearly, it looks like exactly how it's written. Negative 1.96, is that less than or equal to positive 1.67? And is that less than or equal to positive 1.96? All we're doing is finding out if our sample z-score fits between our two cutoff scores. So what we do is we make the comparison. Is negative 1.96 less than or equal to 1.67? The answer is yes. We've confirmed that. Is 1.67 less than or equal to positive 1.96? Then that answer is also yes. So both parts of this inequality are true, which means that we accept, I'm going to say this once, we accept the null hypothesis. But what we really do is we fail to reject it. So I want you to use the language, we failed to reject the null hypothesis because the null hypothesis appears to be supported. If either one of these were not correct or not true, then we would reject the whole thing. But in this case, we have a failure to reject the null hypothesis. We actually don't have a significant result. If a baby walks at 19 months old, that baby does not walk significantly different than the rest of the babies. Let's take a look and see what this looks like as a narrative. We conducted a z-test to determine if there was a significant difference in walking ages between a baby who took an enriched vitamin and babies who did not. The z-score of the sample was not greater than the positive cutoff score or less than the negative cutoff score on the comparison distribution. The z of the sample was 1.67, the cutoff z-score was negative 1.96 and positive 1.96. These results indicate that there is not a significant difference in walking ages between the baby who had the enriched vitamin and the babies who did not. So after all of that, we found that the baby that took the enriched vitamin in this case had a walking age that was not significantly different than the rest of the population. Now, I've talked a little bit about how there is some error built into doing statistics. And what I mean by that is that there are some times where we can make a mistake by making a decision. We call that error. We use a 5% cutoff, and what we mean when we say that is that we're going to accept a result as significant if the result is like the 5% most extreme scores, or if our result occurs less than 5% based on a comparison distribution. There is some built-in error there. Let me ask you a question. What if the baby in the walking example would have walked early without the vitamin? What if the vitamin had nothing to do with it? We just happened to pick a baby that walked really early. We would be making a type 1 error if that were the case. If we reject the null hypothesis, okay, if we say that there is a significant difference in the baby that walked with the vitamin, but that wasn't actually true, we would have made an error. What if the baby in the second example, where we found that there actually wasn't a significant difference, what if the vitamin in the second example actually did have an impact on walking age, but the baby didn't walk late enough for us to catch it at our particular walking age cutoff? What if we were too strict with how we considered our cutoff? That's called a type 2 error, when we fail to reject the null hypothesis when it is in fact false. Let's look at this graphically. Let's look at these cutoffs here. In many cases, we don't know that we are actually committing an error. Social scientists agree that using a cutoff of 5% is generally lenient enough to allow a significant result without over-allowing non-significant results. Let's look at this result here. Let's say that we used a cutoff of 0.4, which is 40%. That's too lenient because somebody could have a score that is only at 1 standard deviation above the mean, and we would think that that's significant. That's just too lenient. We're going to get what are called type 1 errors, where we would say that we have a significant result when we actually don't. On the other hand, if we set a cutoff at 0.5%, meaning half of 1%, that would be too strict. Somebody who scored 2.5 standard deviations above the mean would not have a significant result, even though that is probably a very significant result. So when we set our cutoff values, what we're saying is we're balancing being too lenient and being too strict, and saying that if people respond at 5% or lower on our comparison distribution, then we will consider it to be a significant result. Here's a handy table that helps us to understand type 1 and type 2 errors. If we concluded through our hypothesis testing procedure to reject the null hypothesis, and the research hypothesis is true. So if we reject the null hypothesis and the research hypothesis is true, then we've made a correct decision. We've done good. If we do not reject the null hypothesis, or if we fail to reject the null hypothesis, and the null hypothesis is true, we've done good. We've made the correct decision. However, if we reject the null hypothesis and say that we have a significant result, but we actually don't, then we've made a type 1 error, called an alpha error. If we failed to reject the null hypothesis, and the research hypothesis is true, we've made a type 1 error, meaning we did not find significance when there actually was significance. We've made a type 2 error that's called a beta error. We aren't going to get into power estimates and effect size in this class, so what we've talked about in terms of type 1 and type 2 errors is more for your information to help round out the concepts that we're talking about. Knowing that sometimes we can make a conclusion and it can be incorrect, and that using 5% is a way for us to help balance being too lenient and too strict. So that 5% conventional cutoff that we use is how we are able to set a value that allows us to, within reason, reject the null hypothesis when we have a significant result, or to fail to reject the null hypothesis when we don't have a significant result. Now, I know that was a pretty big chapter, but once we do some examples and really get into it, you're going to be in really good shape. In Chapter 6, we are going to be talking about a special situation where we are doing exactly the same hypothesis testing procedure, except for one wrinkle. Instead of comparing the score of one individual baby to the scores of many other babies, we're going to compare the average score or the mean score of a group of babies to a population. And that creates a wrinkle because it's not a fair comparison to compare the mean of a group of individuals or group of scores to a comparison distribution that is made up of a bunch of individual scores, like in this example. We're going to take a look at that. Don't get spooked by it. We're going to step through it, and it really only leads to a change in step number 2 and a slight change to step numbers 4 and 5. So I look forward to seeing what you can do with this stuff and retaining it. And if you have any questions, feel free to reach out.